Hey guys, my name is Ernest and this is Ernest Sciences and Mathematics TV channel. So in our discussion today, we're going to look at the relationship between molar heat capacity at constant pressure and molar heat capacity at constant volume. And this is going to give us a relationship which we are going to rely on, especially in trying to evaluate some of the problem sets that we're going to come across in thermodynamics. So in this specific case, of course, I had mentioned earlier in our first video that we can be able to describe the molar heat capacity in terms of C. So we said that molar heat capacity is the amount of heat energy that is required to raise the temperature of 1 mole of a substance by 1 degrees Celsius or 1 Kelvin. So we can be able to represent this molar heat capacity in terms of C, given as such. So just put it in more legible way. So this one can be represented in terms of a C. So whenever I write the CE, which is the C subscript P, this is going to represent the molar heat capacity under constant pressure. And then when I write a CV, then therefore this is going to represent the molar heat capacity under constant volume given as such. So we're going to consider the relationship that is going to exist between these specific two aspects of the energy or the heat energy, which we are going to consider in terms of a CP and the CV respectively. So we had said that we can be able to give the molar heat capacity in a differential form, and we said that this is basically going to be the ratio between the delta Q and dt given as such from the definition. And from this specific, of course, representation, we have said that we can be able to represent the CV in terms of the delta QV dt, where delta Q subscript V represents the change in heat and the constant volume given as such. And then we had said that we can be able to represent the CP, which is the molar heat capacity under constant pressure, whereby we said that we can be able to give it in terms of CP is equivalent to the delta QP over dt given as such. And from the various discussions that we have had, of course, especially from the first law of thermodynamics, we had said that we can be able to represent an infinitesimal change in internal energy as delta Q, given as delta W plus dE given as such. And of course, that is going to give the relationship between the work energy, internal energy, and of course the change in internal energy given as dE. So at constant pressure, we can be able to represent that specific form of the first law of thermodynamics by giving it in terms of that is because this was in terms of Q, we put Q to be, that's so that we can be able to consider that one. So at constant pressure, we can be able to represent this infinitesimal change in internal energy using dE. And we say that work is a product of pressure and change in volume. So therefore, we're going to have this aspect of work being represented as a PDV, which is pressure times the change in volume given as such. So from this particular case, we can be able to see that pressure can be represented from the ideal gas equation, whereby we had said that we can be able to give a PV in terms of RT. So this is going to represent 1 mole of a gas. Remember, we had said that the molar heat capacity is going to be the heat energy that is going to be involved or required to raise the temperature of 1 mole of a system by 1 degree centigrade or 1 Kelvin. So therefore, considering 1 mole, then therefore from the ideal gas equation, we're going to have PV represented as a product of RT. Therefore, we can be able to represent PDV in this particular case using R dt. Therefore, whereby we're going to have a differential temperature in this specific case, and this is a change in volume. So from this, of course, we can be able to represent, and therefore this specific representation for the change in heat under constant pressure by giving this second aspect of the equation using this specific, of course, substitution. And I'm going to do away with this first part so that we can be able to use this particular space. So if we have this specific equation, then therefore we can be able to write the change in a Q under constant pressure, which is equivalent to dE plus PdV from the ideal gas equation for 1 mole. We're going to have a PdV represented as RdT. So this is going to be RdT given as such. And therefore, we're going to do this. If you try to divide by a dt throughout this specific equation, let's do it and try to see what version of the equation that we're going to obtain. So therefore, if you divide this one by a dt over dt over dt, so the last bit of it is going to give us R. So therefore, this is going to be the delta QP over dt is equivalent to dE over dt plus R. So from this one, I had given an illustration for, of course, the representation of the concept of the Cp in terms of, that is the molar heat capacity under constant pressure. If we try to look at this specific part of the equation, that is going to be representing that specific aspect. So therefore, we can be able to do a substitution and say Cp is equivalent to, and I've given of course, a substitution for the change in the molar heat capacity under constant volume, whereby I said that the Cv can be represented in terms of, so I can just put it here. I said that Cv can be represented in terms of dE over dt. So therefore, if you try to look at this first bit of the equation, then therefore we can be able to represent this one using Cv plus R. So the final equation that we have obtained from this one is going to give us the relationship that is going to exist between the molar heat capacity at constant pressure and molar heat capacity at constant volume, given as Cp is equals Cv plus R, given as such. So I hope that this is going to assist us in trying to find the relationship that is going to exist between the two. And of course, in any case, if we come across it and we're required to use it, then it would be appropriate for us to use this specific relationship using the procedure that we have done. So that is it for now, guys. Bye. God bless you. Catch us in our next video.